Yes. So yeah, as Pierre was saying, I'm going to present a library for the automated transformation of Rocq AST. But first, I'm going to say a bit more about the context and about why we developed this library. So the context is the following. Proof assistants such as Rocq are used to formalize mathematics and verify proof. And to do that, you use proof scripts, and these proof scripts are often brittle, which means that make them hard to maintain and reuse. And the question we asked ourselves was, how can we improve some criteria such as modularity, automation, and the robustness of Rocq proof? And by robustness here, we mean the ability to withstand change, for example, change in the theorem or change in the Rocq version or the library you use. And some work has already been done on transformation of Rocq code. So we found multiple examples of transformation, and each had their own implementation. So we had a towards automatic transformation of Coq proof script, which is by Mago, which implement a transformation which turns oh sorry, misclicked, which turns a proof composed of multiple tactics into a single proof composed using tacticals. So tacticals are like the uh, are tactics which you use to compose multiple tactics. So you have the repeat, try, but you also have um, colon or the square bracket, which you can use to distribute tactics to multiple goals. And this was done using therapy and anonymous pipes to communicate with it. Then we have designing proof the automation in WAC, which is by Shi and all. And they implement the same transformation, and but they also treat partial proof trees, meaning proof trees with errors. So they do this using a custom LTAC grammar, which they use to parse the LTAC. And then we have post-processing of proof scripts to make them more robust by Lozak and Mago. And in this one, they implement the reverse of the previous transformation, meaning they start with a single tactics composed with tacticals, and they try to uh, reconstitute the list of tactics that was that could they try to, let's say, unfold this single tactic into a list of tactic. And th- they also use therapy with anonymous pipe, and then we have code generation via metaprogramming. Uh, Independently type proof assistant. In this paper, they implement uh, they try to automatically derive a function from a functor, function implementation from a functor on type. So for example, on option and on list. And to do this, they use the Rocq OCaml API. So we can see that despite having multiple papers working on some similar goal, they don't use a similar library. They use a very varied implementation. And so that's why we wanted to have like some sort of, let's say, a library that could do this transformation and that could provide some sort of unified interface to write transformation of Rocq proof. So we have named our library Rocqdito, which is an OCaml library, which does rewriting by rewriting the Rocq AST. So an AST is an abstract syntax tree, if you've forgotten. And basically, it supports source-to-source transformation, meaning we start from a Rocq source script and we turn it into another Rocq source script. And we use Rocq LSP by Emilio Galeiro Rezus to obtain the Rocq AST from the files, and our library allow for easy Rocq AST rewriting, because it automatically moves over nodes, adding, removing when we add, remove, or replace a node to the AST. For example, if we add a node in the middle of a line where there is already tactics, the other tactics will be moved to minimize the space used and also to let some space for the new tactic. And it does the same with removing tactics or nodes to be more complete. It's compatible with OCaml standard library function, meaning it's a functional library. It manipulates non-mutable structures, so it's compatible with filter, fold, and map. And the transformation can be implemented as a fold on a proof structure, as we will see in the next slide. It allows for a dual proof representation, meaning we can represent a proof as either a proof tree, where a proof tree is, for example, if you have a tactic such as split, which will generate two goals, the corresponding proof trees will have two branches corresponding to these two goals attached to the split. Or we can represent it as a linear structure, meaning a proposition and a list of steps to prove or not this proposition. It allows for speculative execution, which I'm gonna explain a bit later. It has quoting and unquoting function, meaning you can turn the AST from the AST to a string and a string to the AST, and it's compatible with the latest version of Rocq, which is Rocq 9.0, and earlier version back to 8.17. And how to define a transformation with Rocq Tito? So a transformation is a function that takes a proof as an input and return a list of symbols from remove, replace, add, and attach. So remove, delete the node which is identified by ID from the AST, replace this node with a new node, add, insert a new node into the AST, and attach, place a new node at a position relative to the node anchor ID. So we have two ways to add a node, add and attach, because add is add use fixed position, meaning it's not commutative or associative because we move nodes when we add or remove nodes. So when you add a node, it can move over node, making your future add invalid, or not, at least not what you expected. And so that's why we used attach, but add is still useful because sometimes you want to place a node at the first line of a file, for example. And so we have some current transformation which replace auto with the explicit sequence of tactics it compute. So we get it from info auto, and then we turn it into a list of steps and insert all these steps into the proof script. We also have a simple transformation which merge consecutive call to intro into a single intros. This was done because, well, auto, when it use intro without an S, meaning it will call, for example, 5 times intro instead of a single intros. We have a transformation which remove unnecessary tactics from the proofs, meaning tactics which does not transform the proof state. And we have a transformation, which I'm going to explain a bit more later, which replaces tactics introducing fresh variables, for example, intros, with intros v1 to vn, where each vi is an automatically introduced variable. So let's talk a bit about, let's zoom on this transformation, sorry. Replacing tactics, introducing fresh variable automatically with a fixed version. So on the left, we have a version with automatically introduced variables. So we use Rocq to automatically introduce all variables. So this is a theorem about factorial growing. And for example, in the induction, we automatically introduce the induction hypothesis and the variable. We also have an inversion and an intros where we automatically introduce H, MO, H1, and HO. And so on the right, we can see, we can also write the version on the right, which fix the variables names, meaning if you change some stuff, or if inversion fresh variables name change between the version of the right will still work, and the version of the left could break. And it's also true about induction hypothesis name, because if you change the variable name, for example, if you do renaming, you have to be careful about renaming the induction hypothesis as well. And so to write this transformation, we use speculative execution, meaning we have a pure function that takes a state S and return a state S1, which is equal to the state after applying the tactic to S. But also this state is wrapped in a result, meaning we can try to run tactic that will fail. This is useful, for example, in turning tactics in trying tactics. And the idea is that for each tactic Li in a proof L, we compute the state Li and the state Ly plus 1, and the method is we take a proof state after each state, run our function on that proof state to get the new state, and extract the variable name before and after. And that's what we use to write our intro transformation, meaning to zoom in a bit. So I'm going to talk about intros, but this is basically applicable to any tactics that introduce fresh variables using Rocq, because what you have to do is change how you write the new tactic, but the logic is still the same. So first we identify the intro tactics, meaning we quote each proof dot and we check simply if its string representation is intros. And as intros automatically introduce variable to the context to get them, we track the proof state before and after the execution. We get the variable before, the variable after, and we get the new variables by subtracting vprev from the intros. It's a tad more complicated in reality because you have to also keep the order of the variables, so it's not just a set subtraction, but that's basically the idea. And to construct our new steps, we concatenate the names of the new variables to intros. So for that, we use quoting. And we quote it into an AST node and wrap it into a replace step, which I presented before. Sorry. And the final result is a list of replace steps for each intro tactics. And yeah, that's basically it for the presentation. So in summary, our goal was to improve the maintenance and robustness of Rocq proof automatically. And our solution is automated transformation of Rocq proof defined by the user. And the result is a library that allows user to write transformation and some simple transformation example. The library is available on GitHub, so you have a link here. I could put it in the chat if you want as well. And we also have future projects, such as automatically constructivizing GeoCoq, which is a Coq library to do geometry. So for that, we have to replace a bunch of tactics with constructive version, and we presented an early version of this work at ADG, which is automated deduction in geometry. And we also want to explore other forms of representation of proof, such as I-proof, which is a hierarchical proof representation. And yeah, thank you for attention, and if you have any question.